Hello guys, so today we'll be learning about electric circuits and various laws that help us to solve problems related to this. So just let me quickly draw a diagram for you guys of an electric circuit. So suppose this is a battery, an ideal one, and this is a resistor, and the circuit is a really simple one, it ends over here. So the EMF of this battery is, let's suppose, 5 volt, and this is of 2 ohm. The resistance is of 2 ohm. So basically this is an electric circuit. Let's suppose this is the battery and this is the resistance. We already learned what a battery does and how it creates potential difference across the circuit to facilitate current flow. So let's begin by learning what a battery is and how the EMF of the battery actually works. So there are two types of batteries. One is a real battery, another one is an ideal battery. So the EMF of an ideal battery is always equal to the potential difference between the two terminals. We can write this as V term. And for real battery, some portion of the total EMF is lost when we measure the V terminal, which being small portion is lost. Let's suppose this is V small of r. This is being lost due to the internal resistance present in the real battery. So we know that potential difference according to Ohm's law is IR, but here the R is small r because we know small r, we are considering small r as the internal resistance of a real battery. So let me just quickly show a diagram. Let's suppose this is a battery, and this is an internal resistance inside the battery, and this is the positive terminal and this is the negative terminal. So this is smaller, this is the positive terminal, this is the negative terminal. This is like a figure of this real battery. And for ideal battery, we can just express it like a positive terminal and a negative terminal. There is no internal resistance, which means the EMF is always equals to the potential difference between the terminals. So let's do another thing. Let's derive another equation for V terminal for the real battery, which will be from this portion. We can write that the EMF, the EMF subtracted by the lost potential for a real battery, this is equal to I times R. Why is it so? Because if you consider a real battery, let me draw a quick figure of a real battery. We can write it like this, and a positive terminal and a negative terminal. So this is a real battery. If we just connect one resistance over here, this is the positive end, this is the negative end, we can say that the potential difference of the terminal between this point, here the potential stays the same, here the potential stays the same because this is a node. Here potential drop occurs, which is equivalent to I times R, where R is the resistance of this resistor. Then the potential difference stays the same up to this part. So the V term of this circuit, which contains a real battery, is I times R. So we can say delta V term is equal to I times R. So from this we can write this portion, and from the theory that we learned over here, we can write this. So we can express the EMF as I R plus I R. If we take I common from here, we can write E equals to I times big R plus small r. This will be small r, my bad. And we can find current equals to EMF divided by the resistance of the circuit and the internal resistance of the battery. So Now if we take a look into Kirchhoff's two rules, we'll see that the first one is called, just make it a little bit bigger. The first one is called KCL, or Kirchhoff's current law. This is also called junction law, and the second rule being KVL, which is Kirchhoff's voltage law. This is also called the loop law. We'll see why these are called this in a minute, but let me just state the law. One deals with current and one deals with potential difference in a closed circuit or a loop. So if we start with Kirchhoff's first law, or current law, KCL, this states that the summation of ingoing current is always equal to the summation of outgoing current in a junction. So this is KCL. So why is this equal? So we know that charge is conservative. Charge is always conserved. Charge is conservative. Charge is conservative. That's why we can write that the amount of ingoing current is always equals to the amount of outgoing current. So what's a junction to begin with? Junction is a point in a circuit where the current can divide into multiple parts. So for example, let's say I1 current is going to this point, and it splits up into I2 and I3. So this point will be considered as a junction. And according to KCL, we can write the summation of ingoing current is equal to the summation of outgoing current. So we can write this as current is scalar. We can just do normal addition or subtraction here. So this is KCL, and if we take a quick look at an example regarding KCL, we can see here that, my bad, we know that current flows from high potential to low potential, or it follows a potential downhill path. So this is the plus terminal, this is the plus terminal, this is the minus terminal. So current will flow like this. Oh my bad, we have to consider here two batteries are present, this one and this one. So this is the more dominant battery, so we'll use this to determine the direction of the current. So this is the plus terminal, this is the negative terminal. So current will flow like this, which is the same as before. And here we can see that there is no junction, right? So the current will flow from here to here. This will give a potential drop from here to here and continue. But if a junction is present like this, we can apply, which is called the KCL, or Kirchhoff's current law, which states that, let me just quickly determine the direction, which says that current will go from here. Let's suppose this is I1. This I1 current will flow, and from here I1 will divide into two parts, one being I2 and the other being I3. So this I2 will pass from this and reunite with I3 and again give us I1, which indicates that charge is conserved. So using Kirchhoff's current law, we can write that I1 is equal to I2 plus I3. So we'll get back to this later after we have learned what KVL is. So let's learn what KVL is. KVL is basically Kirchhoff's voltage law, which is used for a loop. It's also called the loop rule. So whenever we see a loop, we can apply this rule. This comes from the fact that energy is conserved. You know that energy is always conserved. So for electric energy, this should also apply. Let's say that this law states that the potential difference of the loop is equal to the summation of all potential difference, which will be equal to 0 as energy is conserved. So we know that we can verify this by using this concept that when the net displacement is 0, then we'll get this. And we can also apply Stokes' law from here and we can write this, which is basically Stokes' law, which says that electric field is conservative. So what is it conserving? It's conserving charge within a loop. So it's conserving charge within a loop. Alright, so we can also justify this as if the electric potential divided by charge, we know this is equals to potential difference. So potential difference of a loop, when it's 0, this means that this part, the electric potential, is also 0. So there are a few rules when applying KVL. So first we have to, the rules are, I'll write them simply. Rules for using KVL. First is we need to draw the circuit. First of all, this is the most important process, we have to draw the circuit. Then we have to assign a direction to the direction of the current. Sorry. Then we have to travel the loop. So these are the main 3 steps. There are some sub-steps under traveling the loop. Like we know that if you are traveling in the direction of which the current is flowing, we can say that current flows potential downhill, right? Current flows in the direction of potential downhill. So let's say current is flowing. Here there is no potential change, but when it encounters a resistance, if this is the plus side and this is the minus side, then there will be a potential drop over here, which will be negative, as it is going to potential downhill. So we can write when traveling the, like when we are traveling the loop in the direction of the current, we can write that delta V, whenever there will be a potential difference, it will be minus I times R, which is negative because it is going in the direction of potential downhill. And if this is in the direction of current, if we are going in the direction of current, if we are going in the opposite direction, then this will be positive as we are going in the direction of potential uphill. That's why the change in potential will be positive. So these are the rules. Oh, there is another rule, which is the EMF rule. This is almost similar to this rule of delta V. Let's say this is a battery. Let's say that here there is another battery. Let's imagine this like this. So so this is 5 volt, this is 10 volt. So we are traveling from here. Whenever we enter this, then say this is the positive side, this is the negative side. So we're jumping from positive to negative. So the delta V will be minus the EMF, which is minus 10. Suppose we are going in the opposite direction, where we're jumping from negative to positive, which is potential uphill. The delta V will be plus the value of EMF, which is 10 volts in this case. So we have to keep this in mind, all these things, when we use KVL in a closed circuit or loop. So now let us talk about let us talk a little bit about energy and power. So the main goal of electric circuit is to get power or utilize energy, something like that. So we know that the chemical energy is converted into some sort of energy, which is the potential energy, which is later converted into kinetic energy, which gives off thermal energy, which is heat energy, due to the friction and resistance and all. So this part occurs in the conductor, and this loss of energy is known as energy dissipation. And we can also write that the power derived from the battery will be equal to, power is energy, conversion of energy by time. So for this case, the conversion of electric potential energy with time. We know that electric potential energy can be also written as I times, this can also be written as the EMF times U divided by delta T, right? And just a moment. And we know that we can write this as I times the EMF. So the unit of this will be joule per second or watt. You can use whatever you want, because we know that delta U is equals to delta V times charge. So we can use this and apply it in this, and we'll get that the power of the battery is I times the EMF of the battery. So this is the delivered power, what the EMF is delivering to us. This is the delivered power, the battery, which is I times the EMF. And the power which is dissipated, we can write it as P of R due to the resistance. We can use the same path. We can write it as delta U by delta T. We can write delta U as delta VR times Q divided by time. And we know this is ultimately the current times this delta VR. So from here we can write that the power which is dissipated is equals to I times delta VR, and we know that this delta V can be also represented as IR according to Ohm's law. So we can write this as I square R2, and again we can write I square as V by R. So we can write this as V by R squared times R, which will give us, delta V by R squared times R. This gives us delta V squared by R. So we can write the dissipated power as the product of current and potential difference. We can also write it as the product of square of current and resistance. We can also write it as the square of potential difference divided by the resistance. And its unit, like this, is also joules per second or watt. So that's it for today. I'll try to provide the solution of some maths regarding the circuits and how we can apply this KVL and KCL in those circuits to find out current, resistance, anything you can want. Thank you.